Here's the start of part 2 of our 6.1 video, Vectors in the Plane. So this first concept we're going to look at in this video is unit vectors. And so a vector that has a magnitude of 1, its length, in other words, is 1, is called a unit vector. Kind of like the unit circle is a circle with a radius of 1. A unit vector has a magnitude of 1. To find a unit vector u in the direction of another vector v, what you're going to do is say that whatever that vector is, we're basically going to divide both of the components by the magnitude of that vector. And if we do that, it works out that it's in the same direction as what our original vector was, but it has a magnitude of 1. So let's try this example. In order to do this, we have to figure out, to start off with, what the magnitude of this vector is. So we do that, remember, by basically using the Pythagorean theorem. Say 3 squared plus 1 squared, and take the square root. So that's 9 plus 1, which is 10. So the magnitude of v is the square root of 10. And so what we're going to do is, technically we don't have any sort of scalar division defined for vectors. So what we're really doing is we're saying take the reciprocal of the square root of 10, which is 1 over the square root of 10, and let's multiply that by our original vector, 3, 1. Okay, when we do that, that's going to give us 3 over the square root of 10, comma, 1 over the square root of 10. Or another way of writing that is to rationalize, which is optional for us. At least it depends on your teacher. But if we were to rationalize, it would look like this. Oh no. Square root of 10 over 10. Okay, there we go. So that would be the unit vector that's in the same direction as the vector 3, 1. And just going to throw in a little reminder that of what I said earlier. Remember that if I can write a vector in this form, or if they ask me to, I can write it with i's and j's, where I just say the x value of my vector times I plus the y value of my vector times j. So remember that either way they want us to write it, it's no problem, because they're just saying the same thing. Direction angles. So there's a green box in the book that says resolving the vector. If v has a direction angle of theta, the components of v can be computed using the formula v equals, notice we've got the magnitude of v times cosine of the angle, comma, the magnitude of v times sine of the angle. So that's not so bad. So we've got an example here. So if I want the components of this, basically what's going on is we're making this into a right triangle and using the fact that this could be the adjacent side and the opposite side and the hypotenuse, and then working out our right triangle trig. But it's pretty easy to remember this formula, so you don't actually even have to draw the triangle or even think about it. But the magnitude of this is 5. Okay, so the v in absolute values is 5, and the direction angle is 20, and so we just need to fill this in. So 5 times cosine of 20 degrees, comma, 5 times sine of 20 degrees. And then that requires your calculator. Now notice that we are in degrees, because look, it says 20 degrees. So make sure that you aren't trying to use radians on this. And all of our vector stuff should be in degrees because it's such a real-world application kind of scenario. So if we round to the nearest tenths, this would be 4.7, comma. Again, I'm putting this into the calculator. I'm not making these numbers up. I'm typing in 5 sine 20 and pressing enter, and I get 1.7. So this is the component form of the vector that has a magnitude of 5 and a direction angle of 20 degrees. So that's pretty simple. Now, if they give us a vector in component form, and they want us to find the direction angle of the vector, okay, finding the magnitude is really easy. On any of these, if we wanted to find the magnitude, we would just have to use the Pythagorean theorem, and it'd be really easy. But finding the direction angle can be a little bit trickier because, oh, I messed up and didn't close my parentheses here. It requires more thought, basically, because the vector 3, 11, okay, we need to make sure we realize that that is in this first quadrant. So we would go up 3 and up 11, and sure, that'll work. So we start in the middle, and it looks something like this. And so we're basically saying, hey, what is the angle from 0 to get to here? In the first quadrant, that is really easy, because all we have to do is say, hey, if this was a triangle, then this would be, or even if we're not thinking of a triangle, we talked about when we did trig that if this is my x and my y value, I want this angle, then tangent of an angle equals my y value over my x value. That's on our unit circle card somewhere maybe. That tangent theta equals y over x, which means I can do the inverse tangent of y over x, and I will get my angle. Okay, the problem is that inverse tangent is limited on the calculator into only telling us these two quadrants. Okay, so the first quadrant, it's going to be fine. We're going to put into the calculator the inverse tangent of 11 over 3. So make sure you're still in degree mode, although why you would have switched, I have no idea. That gives me 74.7. So this direction angle is 74.7 degrees. Okay, and that makes sense, right? That looks like it could be a 74-degree angle. No big deal. Now let's look at the next one. -3, 4 is in the second quadrant. So we would start at 0, 0, go left 3 and up 4. These are not to scale, so please don't judge them. Okay, something like this. So here we want to know what is the angle to get from 0, which is over here, wow, to this line. What is that angle? Well, we know it's going to be 90. It's going to be in between 90 and 180, right? Inverse tangent doesn't tell us angles in the second quadrant. So here's what we're going to do, is we're going to take the inverse tangent of 4 over 3. Now I know that this is -3, but trust me, it will be easier if we ignore the negatives. Let's do second tangent 4 divided by 3. I get 53 degrees. Now, well, 53.1. That's this angle right here. That's that reference angle is 53.1 degrees. So really, what I want to do is 180 minus 53.1 degrees, and that's going to tell me what my angle is. Okay, because I'm not quite to 180, I'm 53.1 degrees shy, so that's 126.9 degrees is my direction angle in the second quadrant. So basically, anytime you're in the second quadrant, you're going to do 180 minus whatever you get from the inverse tangent. So let's look at the third quadrant here. So we're starting at 0, 0, we're going left -15 and down 2. So something like this. On this one, we are going around 180 degrees, and then whatever this reference angle is, we would add that to 180 degrees. So again, let's not worry about the negatives, although in this case they would cancel out anyway. And let's do inverse tangent of 2 over 15. So that gives me 7.6. So basically this angle right here is 7.6 degrees. So what I want is 180 degrees plus 7.6 degrees. That's going to be this angle. That's pretty easy to add together. That's 187.6 degrees is my angle for that vector. Okay, and then last but not least, we have 7, -2. So write 7 down 2. So something like that. So now this one, if we do inverse tangent, is going to give us this reference angle right here. And so what we need to do is 360 minus that, because it almost goes all the way around the circle to 360, but we're shy whatever that reference angle is. So I'm going to do inverse tangent of, now I'm going to ignore the fact that those are negative and just put in 2/7. Although it really doesn't matter which way you do it, but I get 15.9. So this angle right here is 15.9 degrees. And so I need to do 360 degrees minus 15.9 degrees and see what I get. I get 344.1 degrees. So that is the angle here in the fourth quadrant. Now let's say that you don't ignore the negatives. Sorry, I was reading what my computer randomly told me. Let's say we put in the -2. Second tangent -2 divided by 7. What that changes is it gives you a negative 15.9 because it's saying, hey, I know what that is. It's negative 15.9 degrees. And so you can still hopefully come up with 344.1 degrees. But over here, when it gives you that negative, I mean, I guess you could figure out what that is, but I just like to ignore the fact that there's negatives there. It's really up to you what you want to do on that. So that's how we could find the direction angle in each quadrant. Now the last part of this is going to be real-life applications to what we can do with vectors. And so if you've had physics, then you may have seen questions that are similar to this. And if so, then that's awesome. If not, then you'll be fine anyway. So we have an airplane flying on a compass heading or a bearing, which remember that's where I don't know what's going on. There we go. That's where we look at a compass and we start with 0 up here and then we go this direction in our circle. Okay, so 170 degrees, we're starting at 0 and then going to the right 170 degrees. It's going at 460 miles per hour. A wind is blowing with the bearing 200 degrees at 80 miles per hour. So it says find the component form of the velocity of the airplane, find the actual ground speed and direction of the airplane. So let's make a picture. So we are starting with an airplane that is going at a bearing of 170 degrees. So I'm going to make my airplane green. If I start at 0 and I go almost 180 degrees, that would be down here. Okay, and keep in mind that my airplane vector should be pretty long because 460 miles per hour is a lot. Okay, now what we're basically going to do is add to this vector the wind, because when you're flying on an airplane, you have the speed of the airplane and the direction the airplane is trying to go. You have the speed and the direction that the wind is blowing, and together those affect where the plane is actually going, at what speed and in what direction. Kind of like in a boat, if you are going trying to go like diagonal against the current, that's going to affect the direction you actually go, things like that. So let's do a new set. Every time I do compass bearings, I like to make this little compass. because I think it helps. And that was not expertly placed, so. There we go. So a bearing of 200 degrees is going to be more than 100. So 200 degrees more than 180 is and this section is quite a bit shorter. It doesn't have to be like scale Tuesday. So what's happening is that the airplane is actually going along this here. It starts at 0, 0, and ends up here. And so in order to actually figure out the ground speed and direction of the airplane, which is part B, we have to add these two together. And so part A says find the formula of the velocity of the airplane. So, first off, we need to come up with these angles as trig angles, because this is a bearing of 170 degrees. What is it if I actually want to start at 0 and go around to here? This is going to 70 degrees, and I'm 10 away from 180. So this is 10. So this is the airplane. 10 more than 270 degrees. The angle for that is 280 degrees. Okay, so it was 170 to get around to here. That leaves us with 10 here. And then we're basically transitioning that into a trig angle instead of a bearing. And then the magnitude of this is 460. So if I put that together to get component form, what I'm doing is 460 cosine 280, comma 460 sine 280. That's going to give me the component form of the airplane's velocity that it's trying to go. So I'm going to use my calculator and type this in, and I'm going to round to the nearest hundredth, I guess. So this is 79.88. And then now to find B, this right here is 20. So we are 20 short of 270, which makes this angle 200. And this, it has to airplane plus. Okay, so we're going to need to calculate 8 plus the negative 170. Some to the right, some down, so that makes sense. But it doesn't want the component points to find the actual ground speed and direction here. So, negatives and firing here. So, the thing right here, 0, so our direction